So hello to everybody from Vienna. So I really regret that AofA cannot happen as an in-person meeting at the University of Klagenfurt, because actually Klagenfurt is my hometown. My mother is still living there, and also I've worked at the University of Klagenfurt for 5 years, so it would have been an opportunity to visit my old university. But anyway, it's now my big pleasure to present joint work with Matjaž Konvalinka from Ljubljana, which is actually not far away from Klagenfurt. And I will talk about first bijective proofs of alternating sign matrix theorems. So this talk is based on the 3 articles you see here. And here's a short outline. So I will start with an introduction with definitions and brief description of our results. Then I will show you some general constructions, which can presumably also be applied to other problems. And then I will say something about some details on our constructions. So an alternating sign matrix is a square matrix with entries 0, plus or minus 1, such that in each row and each column 2 conditions are fulfilled. So first condition is that the non-zero entries appear with alternating signs. And the second condition is that the sum of entries is always 1. So here you see an example of such a matrix. Of course, every permutation matrix is an alternating sign matrix. And the smallest alternating sign matrix that is not a permutation matrix is this one of order 3 that has a -1 in the center. It is known that the number of n times n alternating sign matrices is given by this simple formula. All proofs of this formula are actually quite complicated. So I also need to define descending plane partitions. And for this, I first need to define what it is, a strict partition. So a strict partition is a strictly increasing sequence of positive integers. And to such a sequence, you can associate a shifted Young diagram. And here you see the shifted Young diagram of 5, 3, 2. So it has 5 cells in the first row, 3 cells in the second row, and 2 cells in the third row. And shifted refers to the fact that we have this staircase shape on the left boundary. Then a column strict shifted plane partition is a filling of such a shifted Young diagram with positive integers, such that rows decrease weakly and columns decrease strictly. Then for a column strict shifted plane partition, in order to be a descending plane partition, you need two more conditions. So first of all, the first part in each row has to be greater than the length of its row, and it has to be less than or equal to the length of the previous row. So now you might wonder, is this an ugly condition? Well, actually, this condition implies that the objects are in bijection with certain lozenge tilings, namely with lozenge tilings that have a triangular hole of size 2 in the center and that are cyclically symmetric. So here I've listed all descending plane partitions with parts no greater than 3. And if you count them, you see that there are 7 of them. And now recall that there are also 7 n times n, 3 times 3 alternating sign matrices, namely the 6 permutation matrices and the one that has a -1 in the center. And that's actually not a coincidence, because Andrews showed that the number of descending plane partitions with parts no greater than n is given by the same formula as the number of alternating sign matrices. So our first bijection gives a bijective proof of the product formula. And in order to explain what it does, I need to define some sets. So ASMN is the set of n times n alternating sign matrices. Then we consider a refinement. So it's not hard to see that an alternating sign matrix always has a unique 1 in the top row. And now we fix this 1 to be in column I. Then Bn is the set of all 2n-1 subsets of a 3n-2 set. And obviously the number of such sets is given by these binomial coefficients. And then Bni is again a refinement, so it's the set of all elements in Bn whose median is equal to n plus I minus 1. And obviously the number of such sets is given by a product of two binomial coefficients. And then dppn denotes the set of descending plane partitions with parts no greater than n. So then our bijection gives a bijection between these two Cartesian products. So, and here the important thing to note is that the refinement parameter, if you go from left to right, moves from alternating sign matrices to the B set. And of course, if you take the union over all i's, then you get a bijection between these two sets. So simply the refinement parameter disappears. But now the important thing to note is if you go from left to right, then the order of the alternating sign matrices decreases by 1. And now you can apply this recursively in order to obtain a bijection between this Cartesian product and this Cartesian product. And now you can simply take cardinalities and prove the product formula for the number of alternating sign matrices. So our bijections are quite complicated, but they are totally explicit, of course, and we have coded them. So if you want to look at the code, here is the web page. And here I've given an example for a specific choice of parameters. Then bijection 2 explains the relation between alternating sign matrices and descending plane partitions. So here we also were able to deal with a refinement. So for descending plane partitions, we fix the number of n. So we fix the number of maximal entry. And we construct such a bijection. And again, here note that on the left side, the refinement parameters with the ASM. And on the right side, it's with the descending plane partition. And now we can take cardinalities, use induction, and show that there is the same number of descending plane partitions as there is of alternating sign matrices. Also, this has been coded. Here is one particular example. And now it's time to move to the second part, and I will show you the general constructions. So we work with sign sets. So a sign set is divided into a positive and to a negative part. The size of a sign set is the difference between the cardinality of the positive part and the negative part. The opposite sign set is obtained by interchanging the positive and the negative part. Then there is a natural notion of Cartesian product of sign sets, of disjoint union. And what is very important for us, that we can also deal with disjoint unions of family of sign sets, where the index set is also a sign set. So this will be very important for us. And now it's time to tell you something about our approach. So why do we need all these constructions? So actually we translate some of my non-bijective proofs into combinatorics. And note, with the constructions I've shown you on the previous slide, we can deal with all arithmetic operations except for division. So the disjoint union corresponds to the addition. Opposite sign set corresponds to a negative sign, and the Cartesian product corresponds to multiplication. And actually the fact that we are not able to deal with division is reflected in the fact that we sometimes have these redundant factors. So remember, in the bijection 1, there were descending plane partitions appearing. Also, a priori, this problem has nothing to do with descending plane partition. We just wanted to prove the product formula. So then again, another thing is we are working with sign sets, and of course it would be better, or it would be more natural to only work with sets. But we have to do this because in our original proofs, signs are unavoidable, and therefore it is necessary to work with sign sets. So next I want to give you an example of a signed set, so which are signed intervals. So given two integers a and b, and if a is less than or equal to b, then the signed interval is obtained by taking the ordinary interval as positive part and the empty set as negative part. But if a is greater than b, then the positive part is empty and the negative part is just the interval b plus 1, a minus 1. And the signed sets in our constructions are typically signed boxes and disjoint unions of signed boxes. So signed boxes are Cartesian products of signed intervals. So the next important notion is zijections, which generalizes bijections. So a zijection from a signed set S to a signed set T is just an involution on the disjoint union of the elements in S and the elements in T, such that elements from S plus and T minus are mapped to elements from S minus and T plus. So another way to think about this is the following. So we actually have three maps. One is a sign reversing involution on a subset of S. Then we have a sign reversing involution on a subset of T. And for the complements in S and T, we have a sign preserving bijection. And of course, if we have such maps, then it follows that the size of S is the same as the size of T. I also want to give you a fundamental zijection, which is actually the building blocks for most of our zijections. So again, it's about signed intervals. So we claim that there is a zijection from AC to the disjoint union of AB, B plus 1C. So if A is less than or equal to B and B is less than or equal to C, there is nothing to prove because the disjoint intervals on the right are actually, the signed intervals on the right are actually disjoint. But say for instance, we have this relative order here. Then it turns out that the purple interval AB is the biggest interval. The green interval here is a subset of the purple interval, but it has opposite sign, and therefore this disjoint union makes it disappear, and what remains is this here, and that's precisely the left-hand side. Then we also have a notion of Cartesian product of zijection and disjoint union of zijections. So this slide is not meant as something that you should digest right away. Actually, these constructions are not very complicated. It's just, you just have to write down a lot. But the message is that there are such constructions. Then this is more exciting. So there is also a notion of composition of zijections. So if you have a zijection from S to T and one from T to U, then you can compose them, and the result is a zijection from S to U. And even more exciting is that the special case when S minus and U minus, when they are both the empty set, then you obtain the Garcia-Milne involution principle. So now we finally arrive at our problem, which, as you recall, is on alternating sign matrices. So actually, it is better to work with monotone triangles, which are equivalent objects. So how do I obtain, for a given alternating sign matrix, an alternating a monotone triangle? What I do is I add to each entry all entries that are in the same column and above. If you do that, you will obtain a 0, 1 matrix, and then you record row by row the positions of the ones. So for instance, in this row, we have ones in position 1, 2, and 5, and therefore we obtain this here. So a monotone triangle in general is a triangular array that increases weakly in northeast direction and strictly in south, and also weakly in southeast direction, but strictly along rows. And the set of monotone triangles with a given bottom row, K1, K2 up to Kn, is denoted by MT, K1 up to Kn. And now an important thing to note is that if we drop the condition that rows are strictly increasing, then we obtain the well-known Gelfand-Zetlin patterns, which are also important for our construction. So actually how we defined Gelfand-Zetlin patterns on the previous slide was, this implies that the bottom row has to be weakly increasing, but actually we need more general objects for arbitrary integer bottom rows, and this is explained on this slide here. So, so it's again a triangular array with the following conditions. So for every small triangle, so what do I mean by this? So you have two adjacent elements in the same row, and then the element which is above, in the middle and above. We have the requirement that this element is in the signed interval made of these elements here. And this is a sign set, and what is the sign? Well, whenever the left element is greater than the right element, then this contributes -1 to the sign. And well, then the sign set of all Gelfand-Zetlin patterns is denoted by this here, and it can be shown that the signed enumeration of Gelfand-Zetlin patterns is given by this product here. So then we also need arrow patterns, and arrow patterns are also simply triangular arrays where we now put, where the entries are either of these arrows here, and every double arrow contributes a -1 to the sign, and the sign set of arrow patterns is denoted by this here. And the role of an arrow pattern is that it induces a deformation of the bottom row, as indicated in this example here. So here we have an arrow pattern, and then at the bottom I write K1, K2, K3, K4, and K5, and I have a certain deformation, and let's consider K3. So we look at this diagonal and count how many arrows are pointing towards K3, and there's only one arrow, and we subtract 1, and then we consider this diagonal, and there are actually 2 arrows pointing towards K3, and therefore we add 2, and we denote this deformation by D. And now I'm in a position to finally define shifted Gelfand-Zetlin patterns. So they are just disjoint union over all arrow patterns of order n. Then we consider the deformation that is induced by the arrow pattern and take all Gelfand-Zetlin patterns with this bottom row. And now you might wonder, so why is anyone interested in this shifted Gelfand-Zetlin patterns? Well, actually it turns out that one can construct this surjection from monotone triangles to these shifted Gelfand-Zetlin patterns. And what's the merit of this surjection? Well, from now on, we can always replace monotone triangles with these shifted Gelfand-Zetlin patterns. And that turns out to be helpful. So here again, also this surjection is coded, and here is an example. And so here's how we apply this. So for our bijections 1 and 2, actually that's a crucial surjection here. So a surjection from monotone triangles with this bottom row to monotone triangles with this bottom row up to a certain sign, where we have moved the entry, the bottom entry, the leftmost bottom entry to the last position and subtracted n. And the way how we do this is actually it suffices to show this for shifted Gelfand-Zetlin patterns. It's also complicated, but it's actually it's doable at least. And so these two are probably the main ingredients for bijections 1 and 2. But there are many more steps, and after doing all these steps, one finally arrives at the bijections I have briefly explained in the introduction. And with this, I want to end my presentation and thank you for your attention.